Hello everyone, I am Wen Chao. I am presenting our work, HoW-3D, Holistic 3D Wireframe Perception from a Single Image. In modern computer vision, the task of 3D reconstruction from 2D images is recognized as the main goal, and remains as one main grand challenge. There are many forms to represent the 3D object shapes, such as meshes, point clouds, and 3D wireframes. Compared with other forms, the 3D wireframe provides a parsimonious object and scene representation for object and scene understanding, object manipulation and interaction, and computer-aided design. Extracting the 3D wireframe models is a fundamentally challenging task, especially from a single-view 2D image due to the ill-posed nature of 2D to 3D projection. The non-front surfaces of a 3D object cannot be directly observed with only one viewpoint. Thus, perceiving 3D wireframe from an input 2D image entails estimating the non-line of sight geometry. In the literature, the problem has been addressed in simplified settings that either only aim at recovering the visible lines, learning from the single view line drawing given both visible and invisible 2D wireframe, or assumes a high fidelity. The often dense and accurate 3D point cloud can be computed at a first place. One hallmark of human vision is the capability of perceiving holistic 3D structure from 2D input images in an effective and efficient way. Previous methods distill common sense of the specific class objects as prior knowledge. Then the 3D object shape can be reconstructed by combining the prior knowledge and visible cues from the single view images. For example, Pixel 2 Mesh uses a prior topology to adaptively deform the mesh template to reconstruct the objects from the ShapeNet dataset, which only contains objects of 12 categories. When considering using a single-view mesh reconstruction method to reconstruct the 3D model from our ABC-HoW dataset, its reconstruction performance is dramatically dropped, especially for the invisible parts of the objects, as these objects do not have any semantic priors. As it is shown, the reconstructed meshes cannot even hit the geometry of wireframes, thus posing challenges for the 3D wireframe reconstruction. Thus we propose a new task in this paper. Estimating the holistic 3D wireframe directly from a single-view 2D image without resorting to the intermediate point cloud representation and semantic prior. We call it HoW-3D for short. Humans have the strong power to infer the invisible parts from the visible cues via geometric reasoning without prior knowledge about the object. We term that hierarchical perception process as the Gestalt principles of human vision systems. Thus we aim to find a method that mimics the Gestalt principles, first detecting the visible wireframe as a basis, then inferring the invisible 3D structures from the visible cues, and finally achieving the goal of HoW-3D. We propose the Deep Spatial Gestalt model for the task of HoW-3D. It consists of three components: a bottom-up visible 2.5D wireframe perception module built on a recently proposed holistic attraction field map representation for 2D wireframe parsing, a top-down query-based design for inferring invisible junctions from the bottom-up data evidence built on the transformer encoder-decoder framework proposed in the DETR framework, and an integrative reasoning module for 3D wireframe perception and refinement built on graph neural networks. Given the input image, our Deep Spatial Gestalt model first uses the line segment detector HOP to detect the 2.5D visible wireframe. Then we utilize two parallel encoder-decoder transformers to capture both the contextual information presented in the image features and the geometric information presented in the observable 2D wireframe. In the decoding stage, two parallel decoders share the same learnable queries to yield the hidden junctions. The hidden lines are obtained by verifying the enumeration of all pair proposals of the hidden junction and visible junctions. Then we obtain the initial 3D wireframe model by lifting the 2.5D holistic wireframe, which is finally refined by a graph convolution network. Because there is no available data for the new task of HoW-3D, we present a dataset named ABC-HoW that is sourced from the ABC-dataset. As our main goal is perceiving the 3D wireframe models that are composed of straight-line segments, we select 991 objects that are dominated by straight-line segments as the main physical object boundaries from the ABC dataset. As shown on the left of the slide, for each CAD model, we randomly generated 24 sparse views for rendering. Considering the self-occlusion fact in the image formation process, Some perceptually meaningless viewpoints cannot achieve the HoW-3D even by a human should be removed. We show the example of the perception meaningful and meaningless viewpoint in the right. For each object in the ABC-HoW dataset, we render the images and 3D wireframe models from their meaningful viewpoints for the HoW-3D task. The left side displays a pair of the rendered image and the corresponding 3D wireframe model. The visible and hidden line segments in the rendering viewpoint are marked in navy blue and tan, respectively. Finally, our dataset has 12K samples rendered from 991 objects. We split them into 11,179 images from 900 objects and 1079 images from 91 objects for training and testing, respectively, and the statistic for the number of visible and invisible junctions and lines in ABC-HoW dataset is shown in the right table. Experimentally, we show the visualization results of our DSG model and baseline methods compared with ground truth. For the setting of baseline methods, we firstly consider directly combining the existing single-view 3D shape reconstruction and the 3D wireframe reconstruction from the PointCloud. However, as mentioned before, the low-quality mesh reconstruction results from the traditional single mesh reconstruction method would be violated for precisely estimating holistic 3D wireframes. Accordingly, we directly take the densely sampled point clouds for ground truth mesh as ideal outputs of single-view reconstruction. Then, we retrain the best-performing method PC2WF as a perfect baseline. In addition, we extend the state-of-the-art 2D visible wireframe detector, HoP, to handle the task of HoW-3D. Specifically, we first add another hidden branch with the same convolutional architecture as the original visible branch to directly learn both visible and hidden 2D junctions and lines. Then, consistent with our DSG model, we added a depth estimation branch to obtain the holistic 2.5D wireframe and leverage a GCN to refine the 3D wireframe. We term this baseline as HoP-X in the following. The baseline method HoP-X remains a large gap in reconstructing the invisible parts compared with our DSG model, which demonstrates the key difference between the visible and invisible parts for the task of HoW-3D. The perfect baseline PC2WF can precisely detect 3D junctions, but the line verification module that depends on the features extracted from the unstructured point cloud is prone to misclassify the true positive lines. We quantitatively evaluate our DSG model and baseline methods. The traditional wireframe detector designed for 2D visible wireframes failed to detect the invisible parts of the objects from the single-view images, and this will further lead to failures in the 3D space. That is to say, our hierarchical transformer-based module is more effective to detect the invisible parts than the conventional convolutional detectors. Compared with the perfect baseline that takes the ground truth point clouds as input, our method achieved very competitive SAP scores in the strict thresholds of 0.01, 0.03, and 0.05 for the detected line segments, while being better than PC2WF in a relaxed threshold of 0.07. For the AP of 3D junctions, as PC2WF takes the point cloud captured in the most ideal configuration and they only need to classify the junction points from the dense point clouds, they obtained better performance than our DSG model that needs to fill the invisible junctions from single-view images. We also get better results both on the visible parts and invisible parts compared with HoP-X in the 3D space. In ablation studies, we use the predicted 2D location of the hidden junctions to evaluate the average precision under the threshold 1 and 2. Experiments results shows that both global contextual features and the geometric features of visible lines are important for the task of HoW-3D. We also evaluate the effect of the GCN for refinement. Directly lifting the 2.5D wireframe would lead to very poor performance. The GCN module gets better holistic wireframe reconstruction results than the MLP, which does not consider the structural information. In summary, this paper makes the first step of perceiving holistic 3D wireframes from single-view images by proposing an ABC-HoW dataset and a novel Deep Spatial Gestalt model. Our proposed DSG model takes an image as input to hierarchically learn the visible 2.5D wireframe, inferring the hidden 2.5D junctions from the visible geometry, detecting the hidden line segments, and finally resulting in a holistic 3D wireframe model. In the experiments, we demonstrated that the proposed DSG model is effective to mimics the Gestalt principle for human vision systems to fill the invisible geometry from the learned structures. Thanks for your watching and hope you like our work.